In Chapter 3, we'll be discussing populations and samples, what they are, some starting sample sizes to aim for, and steps we can take to prevent our samples from being biased. This will be the first of 3 chapters exploring topics around inferential statistics. While descriptive statistics is about factually describing and summarizing our data, inferential statistics is about trying to make inferences or predictions from a sample. In statistics, our population is what we want to analyze and learn about. It's items, events, or people with a common feature that we have questions about. Your population could be customer returns, home foreclosures, European automobile companies, sport fan demographics, wind farms, or really any definable group of people, places, events, or things. Your sample is a set of observations of your population used in your analysis. In some instances, you may be able to collect a complete sample where every individual in your population is captured. For example, if you're studying customer returns for your company in 2020, you may have data for every single return. When you have a complete sample like this, your measures can be exact. But often, our sample is a smaller selection of our population. When a company with a large customer base sends out a survey asking customers if they'd recommend their service to a friend or colleague, they can't reasonably expect to get a response from every single customer. The responses might only include a small portion of their audience. Or imagine we want to make predictions. While a company may keep a record of past customer returns, they don't have any data on future returns. In a scenario like this, we can't assume last year's data to match next year's, even if not much has changed year to year. Inferential statistics provides tools to help us understand questions when we only have partial data. These statistical tools won't provide exact answers, but will give us a sense of a reasonable spectrum of possibilities. Large samples are nearly always better than small samples. To understand why, you simply need to remember the law of large numbers. This law states that, as our sample size grows, its mean tends towards the average of the whole population. Basically, the more samples we have, the less likely it is that we get fooled by randomness. This law is frequently illustrated with dice rolls. We all naturally understand that each side of a 6-sided dice has the same probability of appearing, as long as the dice is fairly weighted. Ultimately, because of this feature of dice, we'd expect the average of a large number of rolls to be 3.5. When you simulate dice rolls, getting exactly 3.5 is actually kind of rare. You tend to see some variation from the mean just due to randomness. But how much variation depends significantly on how big your sample is. After one roll, your average is never 3.5. It's not even a possible result. After 10 rolls, it can commonly be quite a bit off. But as we increase our simulation to 50 rolls, then 100, our measures tend to move closer and closer to the real mean. By 200 rolls, you tend to get a number very close to 3.5 in simulation after simulation after simulation. You can also see this in our earlier simulation of 100 dice rolls. Initially, it looked like our dice was biased. But our simulation progressed very close to the mean when our sample size was increased to 1,000. Another thing that happens as we increase our sample size is that the distribution of the mean of our sample changes. Imagine we rolled a single dice 200 times and plotted our results on a histogram. The results would look something like this, with a flat distribution. Now let's roll 2 dice, take the mean, and plot that into our histogram. After 200 rolls, the result looks like this. Let's do this one more time, only let's roll 6 dice and take the average. As we increase the size of our sample, the distribution of those samples begins to reflect the normal distribution. And this isn't just true with dice rolls, test scores, income, marathon times. No matter the distribution of a variable in the population, the means of samples of that variable will be roughly normally distributed. This is known as the central limit theorem. The central limit theorem states that the distribution of sample means approaches the normal distribution as the sample size gets larger, regardless of the shape of the population distribution. This is a beautiful thing. With a large enough sample size, our sampling distribution will be well modeled by the normal distribution. This allows us to apply certain statistical tools, such as the empirical rule, on our samples for any population. Another aspect of the central limit theorem is that as our sample size grows in size, its spread decreases. This makes sense if you consider the law of large numbers. As the size of our samples increase, their mean tends towards the mean of the population. So how big should your sample be? In most business cases, the limiting factor for sample sizes is resources. When budget or resources aren't limited, a general rule for determining sample sizes is that, under most conditions, a sample of 30 or higher is sufficient. If you can push it, 100 is even better. If your budget is a bit more flexible, and you know your population size and desired margin of error, then you can refer to a table like the one below. These general rules and tables are a good place to start. Just keep in mind there are a few factors that might drive you to want much larger samples than what is typically recommended. Wanting a high degree of confidence, like 99% or 99.9%, requires much larger samples. It's also good to use larger samples when you have a population with a lot of variance, like there is with any high-risk investment. Or, if you're measuring for variables that occur in a small portion of the population, you need much larger samples. This could be comparing the 1 to 2% open rates of 2 email sends in an A/B test, or measuring for differences in cancer rates in 2 populations of mostly healthy adults. With these scenarios, you're unlikely to see even one positive case in a sample of 30. You'll need to increase the size by 1 or 2 orders of magnitude, so you're getting a large number of positive cases. Sampling bias occurs when our data is collected in such a way that certain members of our population are either overrepresented or underrepresented. Imagine someone in New York City wanted to know the percentage of high schoolers in the US who own smartphones. They stand outside their local public high school and survey students as they walk into the school. Immediately, there are several potential issues of bias in our survey. We're only capturing students from New York City in our survey. We're not capturing rural students. We're not capturing students from any other areas of the country. And we're not capturing the millions of students in the US who are in private schools or homeschools. There are lots of members of our population which are underrepresented in our survey, so the results aren't likely to represent our entire population very well. When collecting our samples, it is important to do so in such a way that it represents the population as best you can and reduces the chance of bias. There are 2 main techniques to achieving this. The ideal type of sample would be a representative sample, which covers the population, and it adequately represents all the chosen characteristics of the population. This type of sampling works best when we're very familiar with our population and know the important characteristics to control for. A similar approach, which works even when we aren't familiar with our population, is a random sample. With this method, we select samples at random from the population, trying to ensure each member of our population has an equal chance of being selected. Random samples are very unbiased. They can allow us to get close to that representative bias without much guesswork. Some quick examples. The first is for a population of all of Apple's stock prices since IPO. A representative might try to cover all phases of Apple's stock, from it going up to going down and not moving at all. Whereas a representative sample may be prices from 100 random days in the period since IPO. In our second population, we're looking at all our customers in California. And our representative sample is going to survey different types of people in different areas of California, ensuring the proportion we take from rural and urban areas matches the proportion of Californians who live in those areas, and it could also try to match other characteristics like gender or income. And our random sample is just 100 randomly selected customers from California.